Now that you have learned about the basic structure of an energy diagram, its axes, so energy in joules on the x-axis, temperature in Celsius or Kelvin on the y-axis, you've learned that the slopey sections are where the temperature changes occur, so your solid, liquids, and gases are being heated and cooled on those slopey sections, depending on whether you're adding energy or removing energy from the system. You've also learned about the different the phase changes that can occur on the energy diagram. This occurs on the flat sections. So melting and freezing happen on the same plateau. Boiling and condensation happen on the same plateau. Again, it depends on whether you're adding or removing energy from the system. And then, of course, the corresponding melting and freezing points and boiling and condensation points. And you'll also remember that when you were going through a phase change, while energy increases or decreases, depending on whether you are melting or freezing or boiling, condensing, the temperature remains constant while you're experiencing that phase change. Now that you've learned all of that, we can start to actually quantify these changes, whether it be a temperature change or a phase change or some combination of those two. We talked about exo and endothermic and briefly mentioned Q, which is our symbol for heat. So when we solve these Q equations, if we end up with a positive answer for Q, that means that we experienced an endothermic process. If we end up with a negative answer for Q, and we've done our calculations correctly, that just means that we have experienced an exothermic process. In other words, energy has been released from the system. So these Q equations that I keep talking about are used to calculate the heat involved in temperature and or phase changes using an energy diagram as a reference. We intentionally use Q, or rather leave Q as lowercase. Okay. And what are Q equations used for? Again, used to calculate the amount of energy absorbed or released when a substance is heated, it's cooled, goes through a phase change, or some combination of all of the above. So it's going to be your job to read a problem and use the context of that problem to determine what phase your substance is starting in, what phase it might be ending in if it changes, if it's being heated up or cooled down, and that will help you anticipate the kind of answer that you should have at the end of your problem. So there are two main Q equations. You'll notice that they have two symbols in common. All right, so Q equals m delta T Cp, and Q equals m delta H. Q and m, they have in common. Q is heat in joules. M, as per usual, is mass measured in grams. Okay, so your biggest task is going to be to decide when to use each equation, because you're always going to have one of two options. It's either m delta Tc or m delta H. Well, delta Tc is used for calculating the amount of energy absorbed or lost specifically during a temperature change. Okay, so let's discuss those other two variables. Delta T is a change in temperature. Delta means change. You may have seen that in a math class or another science class previously. When we calculate this change in temperature, it is very important that you pay attention to the initial and the final temperature of your substance. Because when you calculate that change, you must take your final temperature and subtract your initial temperature from it. So here's a small example. Let's say that my water, for instance, is starting at 50 degrees Celsius, and I'm going to heat up the water until it hits 70 degrees Celsius. So my final temperature is 70. If I subtract 50, I get, and this is very important, positive 20 degrees Celsius. If I was cooling down my water instead, let's say that I'm still starting at, well, no, let's do this. Let's say I'm starting at 70 degrees Celsius this time, and I'm going to end at 50. My final temperature is now 50 degrees, so I'm flipping them. 50 minus 70 gives me negative 20. That negative sign is going to ultimately impact the sign of my Q value, which would tell me that that was an exothermic process. So that's why that's so important to pay attention to. C, or Cp, is the specific heat for a particular phase for a particular substance. So this was previously defined for you, but it is the amount of energy necessary to increase the temperature of 1 gram of a substance by 1 degree Celsius. Thus the units there down below, joules per gram degree Celsius. So how many joules it takes to heat up 1 gram of a substance by 1 degree Celsius. There's an invisible 1 in front of grams and degrees Celsius. Notice that we have that little subscript, P. P can be S, L, or G, depending on if you're talking about your substance as a solid, as a liquid, or a gas. So you're going to have 3 different constants that you could potentially use in this equation. Those constants, those numbers, those values will always be provided for you. Your task is to decide which one do I use. Well, it depends. Are you talking about a solid? Are you talking about a liquid? Or are you talking about a gas? It's not super difficult, but you just have to pay a little bit of attention and, for instance, use your energy diagram and use the temperature to identify which phase you're currently in. And we'll go through many examples. So this is the equation that Q equals m delta Tc will be used in those 3 slopey sections when you're experiencing a temperature change. You cannot use delta Tc in a phase change in the flat sections because temperature doesn't change. Your delta T would be 0. You would multiply everything by 0, it would go to 0, it would make no sense. When you're experiencing a phase change, to calculate the energy involved in that process, you have to use this other equation, Q equals m delta H. So Q is the same, m is the same. Delta H is the heat of the phase change. If you look at the units, notice it's just joules per gram. There's no mention of temperature. That's because temperature is constant during a phase change. So just the amount of energy that is required to take 1 gram of a substance from either a solid to a liquid or a liquid to a gas, and then also vice versa, the exothermic processes. So there's going to be 2 constants, delta H of fusion or delta H of vaporization. Fusion covers the solid to liquid phase change. Vaporization covers the liquid to gas phase change. Okay, so this is a lot of information and a lot of variables. The best way to go about this is to over-label your graph. Tons of prep work, okay? The more prep work you do before you approach a problem, the easier it's going to be. So let me show you what that might look like. Actually, first, let me show you what the standards for water are. So Q equals m delta Tc. Delta T is something you would calculate. M would be given to you in the problem. And then over on the delta H side, the C and the delta H are those numbers that are going to be constant for a substance and provided to you. So specific heat, Cp. For water, there's going to be 3 different constants, one for the solid, one for the liquid, one for the gas. For delta H, all right, there's going to be 2 different constants. Delta H of fusion between solid and liquid, delta H of vaporization between the liquid and the gas. Notice how much more energy it takes to vaporize a substance, to take it from the liquid phase to the gaseous phase. That is because at that point, you are breaking intermolecular forces to go from the condensed state that is liquid into the non-condensed state that is a gas. So it takes 2,260 joules for just 1 gram of water to make it go into the gaseous phase, which is why, or part of the reason, it takes water so long to boil away. All right, now that we have all this overwhelming information, here's where it gets a little easier. We're going to take this information and we're going to apply it to our graph. So here's your energy diagram. You already know where the solid, liquid, and gas portions are. You know where the different phase changes are. Now, what I have done is taken the 2 equations, right? 2 equations, Q equals m delta Tc, Q equals m delta H, and I have labeled each section of the graph. I would do this if I were you. I would absolutely write this down with the appropriate equation, with the corresponding equation. So if I am heating up a solid, look down at that green section. If I'm heating up a solid, okay, and I'm going to start and end as a solid, I would use that green equation, Q equals m delta T, and then Cs. So that whatever the specific heat is for the solid phase. If I were going to boil a substance, so actually look at my mouse here. If I were going to boil a substance, if I were right here, okay, let's say I'm water at 100 degrees Celsius and I want to turn it into a gas at 100 degrees Celsius, I would use this equation right here, Q equals m delta H of vaporization, okay? The best thing to do is to have this written down and constantly refer to it, okay? And just trust yourself to be able to decipher a problem, okay? So we're going to talk next about calculations using Q equations, but this right here is definitely what you want to have written down and have a decent understanding of. And then we will practice using this graph to make those kinds of decisions, and then also to